our last video, we talked about the Clausius-Clapeyron equation, when to use it, and how to solve for one of the unknown temperature values. In this video, we're going to go over that equation again, but this time we're going to cover how to solve for one of the pressure values when that is unknown. So here's an example question. At standard pressure, methanol boils at 64.7 degrees Celsius. At what pressure will methanol boil at 50 degrees Celsius? The enthalpy of vaporization of methanol is 35.2 kilojoules per mole. So this is a perfect example of a question to use for Clausius-Clapeyron. We are given two temperatures in the question. We're given an enthalpy of vaporization, one of the pressures we're solving for, and the other pressure is standard pressure, which is 1 atmosphere. Now here's what we have to make sure of before we start plugging stuff in. Temperature must be in Kelvin, so we cannot be using degrees Celsius in our equation. Delta H must be in joules per mole. So no kilojoules per mole, because our R value is going to be joules per mole Kelvin, and we need those joule values to cancel out. Here are our values for P1, T1, and T2 then. I'm choosing 1 atmosphere, which is standard pressure, to be my P1. And if that's my P1, then the corresponding temperature needs to be 64.7 degrees Celsius. In order to get it into Kelvin, I just have to add 273.15, which gives me 337.85. Now that means that T2 has to be the other temperature value, which is 50 degrees Celsius and 323.15 Kelvin. So that means I'm solving for P2 in this question, because P2 is the pressure that corresponds to my T2 value. The other thing is that delta H of vaporization is 35,200 joules per mole once I convert it from joules into kilojoules. So let's go ahead and start plugging some stuff in then. I can plug in delta H and I can plug in R as well as my two temperature values. So I'm going to end up on the right side with 35,200 joules per mole divided by 8.314 joules per mole Kelvin, and then that is going to be multiplied by 1 over T2 minus 1 over T1. My units of joules and moles will cancel, leaving just units of Kelvin. So when I simplify that fraction, what I'm going to get is 4,233.82247 Kelvin. You can see that when I multiply that number in with my fractions, the kelvins in the numerator and the kelvins in the denominator are going to end up canceling out. So let's compute what those fractions will be equal to inside the brackets. I'm going to get some decimal numbers. I like to usually calculate these separately rather than plugging them all into my calculator at once, just because it's easy to end up with syntax errors when you use multiple fractions in your calculator at the same time. And then I can subtract those two values. They will subtract to be 0.00013465 inverse kelvins. And when I multiply those together, the units of Kelvin will cancel out, and I will end up with an actual number of 0.5700842. So simplifying the entire right side of the equation before I deal with the left side is generally a good course of action when you are solving for one of the pressure values. Now, if we want to separate the pressures from the ln, I'm going to have to get rid of that ln. So here's an easy way to do that. I'm going to say e to the power of the left side is equal to e to the power of the right side. The reason why I am doing this is because of a certain log rule. If you take e to the power of a ln, then that will be equal to whatever was inside the ln. So e to the ln a will be equal to a. Therefore, when I take e to the power of the left side, the e and the ln are going to cancel. And that's just going to leave me with P1 over P2 is equal to e to the 0.5700842, which is equal to 1.768416. So now it's much easier to solve for my P2 term at this point. I just have to rearrange the equation so that P2 is isolated and P1 over 1.768416 will be equal to my new pressure. So P1 was 1 atm. So when I plug this in, I will get a P2 value of 0.565 atm. And that is how we solve for one of the pressure values. So you want to make sure that you are comfortable with your log rules, because that is going to be a really important part of being able to isolate those pressure values.